happy Friday morning. Thank you for being here. I know it's tough in the morning and like it's Friday and you've been spending like the whole week learning and like being at the lecture. So well done, good job. Okay, so today I have two lectures and they're kind of like separated. This part I will talk about some other protocols. So we heard about QKD and device independent and this kind of thing. So I'll tell you about like other protocols on the quantum internet or quantum network that are interesting. The next lecture, I will talk about different assumptions and things like that. So it's a bit more like foundations of crypto, I would call it. And this one is more on protocols. Okay. Hopefully I will not take the whole 2 hours. I don't have too many things to tell you because I wanted to spend time on each one of them. So we'll see. So we'll talk about these three protocols specifically, and I will also want to tell you, like, introduce you to some others more broadly. Okay, so the title of this one, I put it as, so the first one was Power of Quantum Information. I called this one Limitations of Quantum Information. It might be a tricky title or something. You will see why I will call it that maybe when we move along. But I thought since I call it that, it's not a bad idea to do a recap on some of the no-go or some of the things that we've seen together that put some sort of bounds or limits on the amount of information we can extract or things like that. So let's do a quick recap. So we had no cloning, which, as we know, was very important. And so one thing I wanted to tell you is that no cloning is the most fundamental and the most important no-go theorem in quantum information, but there are other no-go theorems as well. So no cloning has a dual or something like that. That's called no deleting theorem. There's also another theorem called no broadcasting theorem. And so this one you probably don't know because it's less famous than the other one. And there's also a theorem about no superposition. Whatever that is, I'm not gonna tell you. If you're interested, come and ask me like in the break. Okay, then we saw these two things which are related. I wanted to remind you because you're going to see it again today. That there's a bound on how much information you can extract from a quantum system, and there's a bound on how well you can distinguish two non-orthogonal states, which are interesting. One thing I didn't talk about, but because we talked a lot about entanglement, I wanted to tell you that there's also bound on entanglement, like how much entanglement you can get from something that's like less entangled. So in general, entanglement is a resource. You can think about it as a resource. And it's a resource in the sense that you have some quantum state that have a lot of this resource, like for instance, maximally entangled states. And then you might have some other states that are still entangled, but they have less of this resource. And if you think about it this way, then you can think about processes that you can give them like low resource objects. And this process will give you a like high resource object. But because this is a resource, there's going to be a price. And you will need to use a bunch of this like low resource state to get like a more resourceful state. So this is also something that I want to tell you because there's also like fundamental bounds on how well you can do that. And so these are all these, but these are all good as we have seen for quantum cryptography. But one thing that happens is that, well, yes, sometimes because our adversaries are also very powerful and they can do non-trivial things when they have access to quantum systems, there are some levels of security in some functionalities that we cannot achieve. And we will see a little bit this today. But before I tell you like the bad news or the things that we cannot do in quantum cryptography, I want to tell you what we can do in quantum cryptography. What is beyond QKD that we can do? And the best way I can tell you this is that there is a zoo of quantum protocols. So you can go on this website, or you can just go simply and search quantum protocol zoo. And somewhere in that website, you will see like a big graph like this. And if you zoom in, you will see something like this. So these are like all of these layers, there's functionalities that you can do, and these are all quantum protocols. So these two layers are all quantum protocols, and it goes on. So it's like a lot of protocols. And so what this graph shows you is that how different quantum protocols implement a certain functionality. Like for instance, if you want to share a key, QKD is one of the protocols that does that for you. And there's many QKD protocols and things like that. So yeah, this is a very good resource, I think. I thought that for you to go and have a look. And in fact, so this, I can tell you a bit of like history of this this website. So this was part of a European project called Quantum Internet Alliance. And when I was a PhD student, I started working on this with some other people, and we built this library. And then, like when we were building this, we realized that, well, okay, so quantum protocols, maybe we don't have a standard for them in the same way that you have like a standard for like classical internet protocols or things like that. But there's still a lot of structure. So there's a lot of like, basically it's not like quantum protocols, even though they're very different, they're completely random. So they still follow some logic and a structure. And this is something we try to capture. So in general, the one way you can think about a hierarchy of how protocols are linked together, you always start from functionality. What is a functionality? Functionality is what you want to do, right? So what you want to do in real life. For instance, you want to share a key, or you want to do digital signature. Digital signature is a functionality. Or you want to flip a coin. This is a functionality. This is something you want to do. And a protocol is something that implements that functionality. For instance, QKD implements that functionality, right? So secret sharing is a functionality, and there are like some secret sharing protocols that implements that functionality. If you remember what I told you about abstract cryptography 2 days ago, the same sort of mindset comes from there as well, right? So you remember you had resources, and then you had ideal functionality, and you had protocols that were using these resources to implement that ideal functionality. This is some sort of like the same mindset. And then you can break down protocols into, so sometimes protocols use some other protocols as a subroutine. And so there's like a hierarchy. There are like lower level protocols, and those protocols, maybe they use another subroutine. And this is in general how also classical protocols are being built. And if you look closely enough, and if you look at enough quantum protocols, you will see that they also follow this kind of structure. So yeah, so this is something that's there. You can go and explore, and I suggest you do that. And what I wanted to tell you is that so now this protocol zoo is on a new website that's called Kagora. It's our new project. It's a community-based resource for a lot of these kinds of zoos, you know, where you gather this knowledge, and community can come and contribute, and you know, put like knowledge and stuff there. So the version 2 of the protocol zoo is going to be here. There will be other zoos as well. So there's like a zoo for quantum programming languages, for benchmarking methods, and things like that. And so when you go to the Kagora website, which you can go, I put the QR code, and you go to the protocol zoo part, you know, it explains what is the protocol zoo, what's the idea, what you can do. And so when you go to each protocol page, you see something like that. So like from here, you can see what kind of things are there. So you can read a short description of the protocol, and you can, you know, read the outline, but the important parts are here. So, you know, when you read a paper about the quantum protocols, there's a lot of information there, but they're kind of like, you know, compact, and it depends on who writes the paper. And if the physicists write it, it's going to be very different from how computer scientists write it or how mathematicians write it. And the idea of the protocol zoo is to kind of like unify this sort of knowledge in a way that's accessible for people, for different levels of knowledge. So you can like just read the description of the protocol, you can read the outline, But you can also read like technical description, you know, like a step by step what this protocol does and how it does it. And you can also like, so when there is a protocol on the website, you also look at the assumptions. So as I keep telling you, every protocol, every crypto scheme has a lot of assumptions. So it's very important to know what are those assumptions. So this is something you can see. And also requirements. So this is something that's important, for instance, for experimentalists, because if you want to go and implement a new protocol from this zoo of protocol, you want to know what it needs to be implemented, and like what physical resources it needs and things like that. So there are things there as well, and like experimental implementation and lots of things. One thing I wanted to tell you, since this is a school and maybe you're looking for a small project to work on after this, or like, you know, while you're at this school, I think it's a good idea. So the zoo is like, the Kagora is very new, and we're still importing stuff from the old zoo to the new zoo. So it's not like if you go to the library, it's not complete. But even more than that, it's not like, there's a lot of new protocols that is not there, and this is supposed to be a community-based resource. So if you know a protocol really well, or if you just, I don't know, want to spend the weekend, read a new protocol and put it in the zoo, this is like a project you can do. And it's quite easy. You can go on the website, make an account, and follow the structure. There's like a lot of explanation to tell you how you should be doing that. And it's not very hard. It's just like, you know, reading a paper really well and try to understand, extract all this kind of like information from it. So yeah, go and do that. Go and put a protocol, or go and read a protocol if you're an experimentalist and you want to implement something new. Go and have a look and have fun. And you can also come talk to me like in the break, or I can show you around, maybe like give you a tour of the website, how it works if you have any questions. But yeah, so this for you to work on. All right, so this is that. But so I put a list of some of the protocols that are also there, and it's good for you to know like what kinds of things are on, like, can be done on a quantum internet. I kind of like broken them into categories. So there are protocols like oblivious transfer, bit commitment, and coin flipping. These are, we cryptographers call them primitives, or like fundamental protocols, or lower level protocols. These are the things that, if you like on their own, maybe they're not very interesting as something that you would do on a daily basis, but they're very important because you can construct things on top of them, right? So that's what they call primitives. I will talk about two of these primitives today, exactly because they're important, and if you know how to do them, you can do a lot of things with them. And then there are this, like a lot of these kind of protocols, which one can name quantum enhanced or quantum function, something like that. So you have secret sharing, digital signature. I will talk about authentication a little bit. You have even like fancy stuff like leader election, when there's like a group of people that want to, you know, make a vote and pick someone as a leader. This is, and you want to do it securely. So this is like cryptography protocol. And there's quantum money, which I will talk about, anonymous transmission. So yeah, lots of things like that. Then there are also higher level functionalities, what I would call them, because these are the things that are more related to computing, but still you want some security property or some cryptography property on top of your computing. So for instance, secure multi-party delegated quantum computing. So, you know, these days, if you go and run a code on IBM, this is delegated computing, because, you know, you're delegating your computation on a cloud to a server. And for maybe a lot of application, it's very important that you can trust this process, and this has been done securely. So that's why secure delegated quantum computing, like that, you should follow a specific protocol in order to make sure when you're delegating a computation, it's secure. There is blind quantum computing, which, if I'm correct, someone next week will talk about that. I think I saw that on the on the schedule. So hopefully you will hear about this a bit. And there are things like verification of quantum computing, which is very important. Because if you have a very powerful quantum computer and it gives you answers that are classically impossible to get, how are you going to check that? And this is a very important and very fundamental question that people have been working for many, many, many years to try to be able to answer that. Because it's fundamentally really hard to do this. Because the whole point is that you're doing something that's not necessarily easily verifiable, and it's supposed not to be doable classically, and we are classical, so how are we going to take the answer? And there's like very, I would say, beautiful and innovative protocols that how you can do this. Yeah, you can even do like voting and stuff with quantum. And so there's another level that I kind of like separate from these guys. And the reason is that there are some functionalities. So, you know, like digital signature or secret sharing fundamentally is not a quantum functionality. It's something you do also classically. So the functionality itself is a classical functionality. You can do it with classical protocols or you can do it with quantum protocols. But yeah. But there are certain functionalities that they are quantum in nature. And so you've seen one of them. So teleportation is a functionality that's quantum. Like, you know, classically, you're not sending a state somewhere. So this is like a quantum functionality somehow. You coded that, so that's cool. But there are other functionalities that you cannot have classic, like they're unachievable in the classical world. There are things like certified deletion, like you send a message and like you want to have a process to delete it and have a certification that it has been deleted. This has been shown not to be doable classically, but quantum we can do that. There are things like copy protection. So they're kind of interesting because they're different protocols in nature, I would call them. Okay, so yeah, by now I think you're convinced that there's a lot more than QKD in the world of quantum network and quantum communication. Cool. So let's start with a bunch of these protocols. I will start with quantum money because this is one of the oldest one and it's quite cool. Before I tell you about quantum money, I want to talk about what is money. so this can be a very philosophical question in some sense, or
you can give us some
political. so I will not. I don't want to maybe get into those stuff, but well, you can say I don't know. It's just a number. It's like an illusion. I would say that in some sense. But okay. So but this is like physical bills, like right. So what is that? What is so special about that? Like, can we somehow capture this in some level of formality? And that's the idea. So the way I would capture this is that, okay, so the money, this like piece of paper that you have and you spend, is nothing with a bank or a mint, you know, something that like some certified authority that gives value to this thing. So there's a bank, then there's a bill, and not this bill. And there's so the bill has a serial number. And usually this is you know, it's been printed on a special paper with a special ink, and well, there's reason for that, right? And so the first important property that this like coin or bill or like things should have is to be able to be verifiable. So there should be a difference between a piece of paper and an actual bill. So when there should be a process that, you know, right, go to the bank, you know, they can check that and say, okay, this is a good one, this is a certified one. So there is the verifiability. The other thing is that if I'm malicious or if I need a lot of money, what I want to do is that I want to like take this bill into the copy machine and like make more and more and more money. And well, so this should be prevented. This is not something that a money scheme wants to have, so this should not happen. So in general, when you're thinking about any money scheme, classical or quantum, if you want to somehow capture properties that are important for money, these are the two most important properties. One of them is unclonability. In classical world, they usually call that anti-counterfeiting or unportability. So that's what it means. It means that you should not be able to copy and get away with it. And verifiability. So these are the two things that we need. So now when we go to quantum, it's very natural for someone who knows quantum information to think about that. Okay, so if unclonability is such an important property and it's really hard to do classically because so things are clonable, copyable in the classical world. So the way we make them uncopyable is just by making the copying process hard, by using a special ink or special paper and things like that, that like not everyone has access to. But if you're a quantum information scientist, you're like, oh, okay, wait a minute, maybe I can use unclonability of quantum state as a money, right? And this sounds like a crazy idea, and definitely in 1969, when Stephen Wiesner was thinking about this, people were thinking it's a crazy idea. But yeah, so that's how quantum money was born. And interestingly, this was introduced in the same conjugate coding paper. So this is like the screenshot of the old paper that Stephen Wiesner did. That he talks about this like conjugate coding, conjugate basis that I talked about it, and Arthur also talked about it yesterday. And in the same paper, he kind of like mentioned this like application of money for this kind of like state. As you can see, I put like it was published many years later, and the reason was that I think the story is that he took it, or he sent it for publication, and people were like, "Oh, this is too sci-fi," and he was like, "All right," shelved the paper, and then it wasn't published until like many years later. And so the idea was simple. It was like, okay, if I have a states, like conjugate basis states that are unclonable because they're not orthogonal, so they're not distinguishable. So yeah, maybe I can use them for money. But so, as I said in the last slide, for money, you don't just need unclonability. You also need verifiability. So we need to see how this has been solved, because without verifiability, this is not a money scheme. So let's have a look. So that's how Wiesner's quantum money scheme works. It's quite simple. So you have a serial number. You had it in the classical one as well, right? So you still have a serial number. Your serial number though has two parts. So for every bit of it, you have 2 bits, right? So I call that X of dollar and theta of dollar. And the way you do it is quite simple. You follow the same BB84 encoding, but there you were just like, one of the bits were the bases, one of the bits was the basis, one of the bits was the actual bits, and you wanted to get randomness out of this. Here you don't want to do that. You just want to do some sort of encoding. So you want to make this state like hard to read. So that's how you do it. You take these 2 bits and you do the same encoding. So one of them bases, one of them bits. And so 0, 0 will be state 0, 0, 1, 1, 1, 0 plus, 1, 1 minus. So this is how you do it. And so then every bill of money consists of a stream of this state. So you have like n number of them, and then this is n BB84 state. Okay, so how do we verify? Well, the verification is not too hard, because if you have the right basis and you always measure in the right basis, you always get the right value, and this is verifiable. So if the bank has this database of serial numbers, I can give you the state, you can go and like do something with it and then come back and tell me, okay, so I want you to verify this is my money, and then the only thing I would do is that I will like take your money qubit by qubit, and I will measure it in the right basis, and so I can deterministically check that this is the right money. So it has unclonability and it has verifiability. So that sounds cool. Okay, so so the verification algorithm, like a bit more formally, takes a money, a serial number, and output accept or reject. But yeah, that's what it is. Okay, but how secure is actually business quantum money? Because we've seen that with the QKD as well, right? So you write the protocol, it seems very secure, but like you need to prove this. So the first trivial attack you can think of is that, okay, someone gets this stream of quantum state, they can measure and try to beat the serial number, right? And remember, if you have the serial number, then you can produce as many money as you want, because that's the whole point, right? You can prepare a state, it's just that you don't know in what basis and what values. So the trivial attack is that you do that. And well, you can probably already guess. This is for every qubit you can guess the right basis with probably half. So this is still fine. There are better attacks though. Does anyone want to guess what is the best attack, or what is the better than half? Probably half attack. Break the quantum money. Yeah, exactly. You can do that as well. So that turns out to give something close to the ideal. Anything else? There's another one, and I assume you have seen that. So the best attack is known to have probability 3/4 for every qubit. So this is still good, right? Even though 3/4 is high, but because you have n number of these things, and you only certify when you accept all of them, right? So if one of them, so this is not very robust, but you know, even if one of them fails, you're like, this is not a good money, right? You will reject. So it needs to succeed in all of them. So an adversary needs to succeed in all the qubits, which means that now you have to succeed here. You can succeed with probability 3/4 to the end, which is still negligible or like small. And the attack is what you've seen already. So you remember you have this intercept resend attack in the QKD? So it's kind of like similar to that. You can basically measure and then make a guess based on your measurement and re-prepare the state. So this doesn't clone the state, but it passes the verification with probability 3/4. So that's kind of like the attack, and that is known to be the best attack on Wizard quantum scheme. Intercept. So here, it's not like this is not a communication, but the idea is that, so let's say the adversary has this stream of money, and so the goal is to extract the serial number or reproduce another stream of money that passes the verification algorithm. And remember, the verification algorithm is just measuring each one in the right basis. So it's more like people several tries of verification. So you only have one of these. If you already had many copies of this money estate, you could break it very easily. So that's not the point. You have only one. But the idea is that, so let's say one of these states, one piece of my money is a plus state, right? And I make a guess about the basis. Let's say I make a guess that if I make the right guess, that part will pass, right? If I make the wrong guess, again with probability half, I prepare a state that passes the verification, because the verification measures in the like if I get 0, then the verification still measures in the x basis. So with probability half, I can still win. So this half plus half times half, which is 3/4. So this is the success probability for every qubit, and then this amplifies if as long as this is IID, as Arthur was saying yesterday. So this passes with 0. So that's it. But so I mean, security-wise, quantum money scheme is still good. It's secure in some sense. But the problem with that is not really the security, if you want, is that this is not really practical if you think about it. And there's like a couple of issues with that. So first of all, you need private verification, which means that the only party that can verify this is a bank. It's not like, so usually this is not how money works. You want every merchant to be able to verify your money, or to kind of, maybe they like, in real life they don't always verify your money, but it somehow needs to be verifiable for merchants. And this is not scalable, because then you need every one of those to already have your serial number, and they're maybe not so trusted, so you don't want this to happen. So yeah, it's like this sort of private verification scheme is not very practical in real life. And then the second important problem as you're an experimenter, like people who are experimenters in this room, probably they were thinking about that already. They were like, yeah, this is not gonna last, right? Because if you have a state, you cannot just like take it with you and come back like 2 days later and try to study. It's going to decohere, so it's not really, I mean, it's very interesting theoretically, but yeah. So there's like the coherence issue. But maybe you don't really use it as a money. You use it as a primitive for other protocol, and in that case, maybe it makes sense. One thing I wanted to tell you is that with all that, quantum money is still a very interesting cryptography primitive, and people these days are working a lot on public key quantum money. So they want to see how they can use the good properties of quantum stuff, but still like be able to build a public key scheme. And here they're not so much worried about like, you know, the assumption breaking down, not breaking down. Still like being able to have that is pretty cool, because unclonability is really an important problem in digital money, and there's no way you can solve it, and quantum gives you a way. So publicly quantum money is really interesting, and it turned out to be very, very hard problem theoretically, and this is still open. So if you're like looking for an open problem to work with, I don't recommend, because it's getting like it's getting harder than you think. And there are some like public key quantum money schemes already, but none of them are like really good. They usually like they use some assumptions that are not so realizable, and people are not very happy with them and things like that. So yeah, but yeah, it's an interesting problem theoretically. Yeah. So the main goal of the attack is to fort, which means that you want to give another state, which is not the money state, but that state passes the verification. Yeah, so if you have one of these and you extract the serial number, because if you have a perfect serial number, you can reproduce as many as you want, then this is like, you know, it gives you that attack. But the main goal of basically the main functionality that or the main cryptography property that you want to attack is the unfortability. So you want to be able to fort.
If you go to block, when you just get another serial number, you'll get another two.
Sorry?
If you go to block, you get a different serial number.
Yeah.
Wouldn't that just be another
so the idea is that, well, your ID with the serial number will be linked, right? So let's say when the bank will give you that, but that's a good question, because what you're asking is maybe like another level of affordability. The thing is that, can I produce a money that will pass as any of them in the database? And that's a different attack, but this is not what we're doing. Okay. Any other questions about money? Yes.
But I want to do the money, and somehow have like also use
Yeah, exactly. So if we do any process on that, it will lead to a different serial. So yeah, spending it would be just to verify it, right? So and it will destroy. It would like, so it's a money that when you verify it will self-destroy. So it's spent already. It's something. Yes.
So my question is about is it possible, for example, it's very, for example, if you bring your money to a seller or something, and is it possible like to do some teleportation from the retailer to the bank?
Yes, but I can't see what you mean. Yeah, maybe, yeah, probably. I haven't thought about that, to be honest, but yeah, it should be doable. But so then you need to teleport all the, so you need to teleport all the parts separately, but yeah, that should be doable. So what you mean is that, like, so you have the merchant, you have the bank, and every time this guy wants to verify, they teleport the money to the bank.
Yes.
They verify, they tell them the result, and then they certify. Yeah, that's I don't see any problem with that. Yeah, you can do that, but you still, you know, like it maybe makes the private verification thing a bit better, but then every party who wants to verify, they cannot just like have the database. They need to do this like teleportation. So they need to have like this quantum technology to do, let's say, the teleportation. You need to have like a channel again between them. I mean, it's a cool idea theoretically, but yeah. So.
It also adds a layer of the merchant, right? So like a integration building spending somewhere else and verify that we can do it. I thought like security guarantee both ways. It will spend it. Spend it. If I give you the money, how do I know that when verify that I'm spending somewhere else?
Yeah. That's a good one. I don't know how long it works.
There's I think there are schemes for that. There's like a quantum credit card thing.
Yeah, there are better quantum money schemes, even like privately. I will maybe mention this one like a bit later in the second lecture, but yeah, there are better private key quantum money schemes. But still, there's this. Yes, so the point is that it's not so scalable to have a quantum money scheme privately. By privately, I mean, to do symmetric cryptography kind of style to verify it. Because then either you need to, everyone needs to go to the certificate authority, which is the bank, to get, the right serial number to be able to check, or you have to do like something like that, or you have to like run some like extra protocol to be able to get around this. And so the whole problem is that this is not so scalable, and maybe for some functionality you don't mind that much, but for if you want the money scheme, then you might. So still, I think if one only thinks about like the functionality, it makes a lot of sense to look for public key functionality. Any other questions? Okay, good. Let's go. So next one, bit commitment. What is bit commitment? So bit commitment is a functionality. Again, like this is like a fundamental functionality in media. So bit commitment is somehow a cryptographic version of a safe box, if you want. That's the best way I can describe it. So usually it has two phases. In the commit phase, Alice will put a bit into a safe box or into some string. So this is commit, and then you send that commit to the second party, which is Bob. And so in the reveal phase, Bob will open the box, but he can't just open it. He needs to wait for Alice to send a message or a request that says reveal. And then reveal shall happen. So you put the message reveal inside the box, and then you get the original commitment, you get the commit, and you get the certification or confirmation that this has been the one that was already in the box. Yeah, so the security of this protocol is described by two things. So there are two properties that you want this functionality to have. The first thing is that Alice cannot change her mind, right? So if I put something in the box, it's not like like that I have a remote control, and like after I send the box, I can like push the remote control and change the bit inside the box. So this is something that should not happen. And the second thing I don't want to happen is that Bob should not learn the bits before I reveal it, right? So if I put the safe box there to Bob for safekeeping, it shouldn't be that he can like open it at any time he wants and know what I did. Why we want this functionality? It's a different story, because as I said, this is like maybe not interesting on its own, but it's a very important thing, and you can build things on top of this. One thing you maybe noticed already is that this is fundamentally very different from QKD in terms of the setup. Because in protocols like QKD, your Alice and Bob are trusted parties. So they're the good guys. The bad guys is always in the middle. Here, there is no in the middle. They're both bad guys. So you're in a setup where you're in a mistrustful setup, in a sense that both of the parties can cheat, and they will if they can, right? So it's kind of like a weird situation, but it might be true in real life. It might be exactly that kind of situation. But this change in the setup, it makes things very hard, and I just wanted to highlight that. Okay, so as I said many times now, bit commitment is very important. It's because it's a cryptography building block, and now I'm finally gonna tell you why. The reason is that it's been shown. It's like an old classical paper. Classical paper that proves that. I should have put maybe the citation. I will put it more correct. But so basically they proved that a lot of two-party functionalities in general, you can build them on top of bit commitment. So if you have a bit commitment, so if you have a protocol that does what I told you, you can build a lot of two-party functionalities. And what are these two-party functionalities? They are things like multi-party computation. So if you want to, like two-party wants to compute something in a secure way, or fancy things like zero-knowledge proofs, which I'm not going to talk about, but you know, look it up if you want. It's probably in classical crypto now. Zero knowledge is kind of like one of the most hot topic things that still people work on. Yeah, so it's like a magical box. If you give a bit commitment to a cryptographer, they will be so happy. They can do so many things with that. So how do you do bit commitment? And this is the thing. So bit commitment classically it's impossible. And this is one of the most important no-goes of all cryptography. And it's impossible in what sense? It's impossible in the information theoretic security. So you remember you're in a mistrustful setup. So information security here means that Alice and Bob, they can both be unbounded in the operations and stuff they do. So they're not like computationally bounded. There's no assumption. Everyone can do anything they want. So in this kind of scenario, you cannot have classically secure bit commitment. You need to add more assumptions to be able to get it. So the reason is that there are two reasons. First of all, because you're not bounded in the operation you can make, you can always do brute force. And if brute force works, then you've broken the protocol. And the second one, which is kind of like more deep, and I want like us to think about it together, is that so the proof kind of shows this, that hiding implies that binding is impossible. So these two properties that you want at the same time, they're just impossible to have. And so let's think about this a bit together. So why do you think this is the case? Like, give me intuitions, ideas. That might not be. So let me go back to this so that you have these two. So this is binding. This is so concealing is the same as hiding. So hiding will tell you that you cannot do binding. So this is kind of like one way of the no-go. So showing that binding it's impossible, it's like that brute force attack thingy that I told you. So if this is actually a safe, and if I give a safe to Bob, and the way Bob can do it is that he can try all possible combinations, and still just break any safe box. So there is no safe box on the board that is like resistance against brute force attack. It's just that we believe, we make them hard enough so that brute force is not feasible. But when you're in the information theoretic world, this can happen. But so the other one is more interesting. Why hiding or concealing implies that binding is impossible?
Because that's a specific key that changes the value of a bit that's Bob happens.
Who has this specific key?
Alice. So if she wants to suddenly change the value that Bob happens saved, so she can prepare like a whole set of keys that as Bob happens saved changes the value. And Bob cannot know that from the get-go.
Okay. Any other? Let's give it a lot. I'll get back to you. Any other ideas? So you're kind of in the right track, but the key was in the last part that you said. So you said like because Bob doesn't know, right? So the thing is that when I say Bob learns nothing about the bit, right? It means that whatever like this box is, whatever I'm sending as my commitment to Bob, with respect to bit C being 0 and 1, it looks the same to Bob. So it should be indistinguishable. Otherwise, I don't have any hiding, right? Does that make sense? So this is the first part. So this is my hiding property. But now what happens is that, well, if I have something that's like completely indistinguishable to Bob, and I have the control to open it in any way that I want, then I can open it to, like I can send my message to open this message to 0 or to 1. And Bob will never know it because it's supposed to be indistinguishable to Bob. So if if my commitment leaks nothing to Bob, then I can change my mind anywhere, anytime I want. And that's the main problem here. Does that make sense? So you can you basically you can think of it that in a way that you're not sending the bit plainly, right? So you're not sending 0, 1, you're sending some sort of, let's say, encryption or something of that bit. But the problem is that Bob, in order to make sure that you already, given him, let's say, 0, needs to have something that that verifies that, right? But if Bob has that thing to verify that one bit, then they can open the box before. They can verify it before you tell them how to reveal. And that's the main issue. So if I have something that reveals no information and I don't have any extra information, this is like part of the assumption. If I don't have any extra assumption, then there is no way that I can have hiding and binding at the same time. And this is like fundamentally impossible.
So like, if I understood this correctly, so what I meant was like classically, if I have like a literal safe, right? So there's the bit inside of it, right? And there are basically two passcodes. One opens the safe, and the other sounds an alarm. And since Bob can't know which one of them could possibly like sound an alarm or open the safe, Alice can at any time decide to change her mind and send the right code or the right passcode or the wrong passcode.
So what is the send the alarm? So what you're saying is that there are two keys that opens this box. So one of them just open it and the other one changes it that opens, right?
Well, it changes the result instead of opening.
Changes the result instead of, I mean, it still needs to open. So if the box doesn't open, Bob aborts, right?
It does open, for example, but
exactly.
still sends a silent alarm to the police.
Okay, so I don't think alarm is part of
0 and 1.
So, but what does the alarm do? That's the part I don't understand.
I mean, technically, you could see it as a different value of the bit.
It's a different value of the bit. Yeah.
So 0 is just get whatever is inside the safe, and 1 is get what's inside the safe, but also go to the list.
Well, yeah, but that's not completely breaking the because like the functionality that I want is to so let's say Alice's perfect attack is what? Is to send this box and well maybe they have some conversation before she decides to open the box, right? And then like if she opens this honestly, let's say the bit was 0. Right? But now she can like maybe change it. Maybe they're trying to do like a secret deal or something, and then Alice changes her mind. Right? So in a secure bit commitment, she shouldn't be able to change her mind. And when Alice changes her mind, inside the protocol, she doesn't have anything else than this like message reveal. Right? So this is how I define the functionality, right? I only send a message and it will open. So the idea is that can I send a message that will open the box to a different value without Bob noticing it? Right? So I mean, so basically, I think the way you're defining it is kind of the same, but you're introducing a third outcome to this, which I don't have.
You can append it to the first one. So like, or as I was saying, like maybe there are two different doors to the safe, so one opens one of them, the other opens the other, and Bob can't see like the doors. They're like so well hidden. And he doesn't even know from which like side the safe will open once he enters the code.
Yeah, I can see that. I think it's kind of related, but like to see that this is exactly the same functionality, we need to write it up. But I can come back to you after the break and have that. But is this clear that why this is impossible? I think your idea of like the reason Alice can change it is kind of like similar to what I was saying. So is this clear to everyone? Okay, good. So we established that the good thing that we wanted and it gives us all the cryptography that we want. Is it possible? Very good. So, right. So how do we do this? But I already have that. Wait. Okay, yeah. So, you can't, blah, blah. Oh, okay. Because I got back to this slide. So how, but, okay, so this was classical. How about quantum? Let's try to do that with quantum. And so I have one slide that summarizes the situation with the quantum. I'll just like let you have fun with it. Yeah, so that's the thing. That came kind of like as a surprise to people because they was like, oh, this is something quantum is good at. It wasn't. Perfect bit commitment is also impossible quantum. This is one of the impossibilities of quantum cryptography. It's been shown by Locho and Mayers separately in this like 2 papers. I think there's 2 or this one. Yeah, I think there's 2. So this is basically that. This is one of the impossibilities. The intuition here is kind of interesting. Is that there are always 2 qubit states. So the reason that this is impossible in quantum is like, so you want to do somehow the commitment through a state, right? So you want to send the states to Bob and make sure that your bit is encoded inside the quantum state before you send, let's say, the basis for it to reveal. And it kind of like feels like it should work. But the reason that it doesn't is that there are always 2 qubit states that Alice can run a local operation changing the other bits without Bob noticing it, because that will be distinguishable to Bob. So basically it will change the local density matrix, and the local density matrix up to the unitary that Alice has performed are the same to Bob. And this is the reason that you can always like break this problem. Sorry. This is one of the problems. Yeah. So yeah, Bob's density matrix up to Alice's local operation. So this will tell you that the commit will break. So the binding will break in quantum. Although you can achieve one side of this. So first of all, classically you can do bit commitment if you add more assumptions. So if you're happy to assume one-way function exists or things like that, then there are some sort of commitment. It's just that information theoretically is impossible. In quantum as well, you can achieve a perfect, like one of these properties perfectly, but the other one has to be computational. So you can achieve, for instance, a statistical binding, but computational hiding or concealing, or statistical hiding and computational binding. So like one-sided perfectness you can achieve completely, but you know that doesn't give you. Okay, that's I think all I wanted you to know about bit commitment. Yes. Do you have any question? Because I think this is maybe the last one. So it's almost 10. If you want, you can go for a break, like a short break, and come back and tell you about the last protocol. Or if you want, we can continue, and then I give you a longer break, whichever way you prefer. Who wants break? Hands up.
So your head was up?
No, I was just like that. Okay, so shall we continue? It's like not all of you want to. Okay, so let's continue and I finish, and then we can go and have a look. Do you have any other questions about commitment? So I realized that I didn't show you a quantum bit commitment protocol. It's because I think they're not super easy and they don't achieve like so. So I think like understanding the impossibility is kind of like more important than the protocol. In the second part, maybe I'll like I give you one way you can do that. All right. So quite quickly. So you solved the question. Now I'm going to give you like another random functionality, and we'll talk about this. We'll see what it gives us. This functionality is called coin flipping. And it doesn't mean that you want to flip a coin. What it means is that you have two parties, they are separated, and they want to flip a coin and agree on a random bit. But, you know, they have to do it over the phone. They're like not in the same place. If they were in the same place, it would be easy, but not, now they're not. And so this is another one of those functionalities that is two-party, and both of the party can be potentially malicious. So they don't trust each other, right? And so the story is of that. So this was introduced in this paper by Bloom in 1983. It's a very cool paper. Like to just go and have a look. I like the paper. So basically the story that's in the paper is a bit sad. So I like to change the story in a more happy one. And the main story that's in the paper is that Alice and Bob are getting a divorce and they want to like decide who gets the child or get the car or something like that. And I was like, okay, that's not a very happy story. That's not the way to sell it. So I was like, okay. So Alice and Bob, they want to go to a road trip, but they're planning it ahead. And Alice is a metalhead. I like metal music, so I was like, okay. So Alice is a metalhead and Bob is Bob Marley. So they cannot agree on what kind of music they put in the car, and they have a very long road trip to take. And then so they're planning it, and they don't trust each other. So they have to like find a way to, before going on this like torturous trip with torturous music that they cannot understand, to agree who's gonna be and put the music in the car. So that's my story. That's how I like say this, like teach this protocol in the class. I don't like the divorce story. Okay. So that's the functionality. So I think, you know, by now you kind of like you will remember this. All right. So if we write this formally, there's a reason I call this the strong coin flipping, because there's a weak one. Otherwise, yeah. So this is the original one. So this is the task. You have two mutually distrustful players, blah blah blah. The goal is to output a bit, a random bit seed that has the following property. So correctness means that if Alice and Bob are honest, then this should be C. Sorry, I don't know why C. So C is uniformly random and distributed, so it's like a perfect coin. And security means that neither of the player, they can force the value of the bits to do something they want, right? So let's say they agree on, I don't know, Alice gets the 0 and Bob gets the 1. So Alice should not bias it towards 0 and Bob should not bias it towards 1. So that's the functionality. And well, so the smallest bias that this protocol will achieve, or like not manage to achieve somehow. So if you have a bias, let's say, the smallest epsilon is called the bias of the protocol. Right? So maybe like you cannot do that with bias 0, maybe you can still do that, but with the bias of 10 or not. Okay. So this protocol is also impossible classically. So there is no classical, so there is no way that over the phone we can do this. No matter how much of a complex, weird, classical tool and technology we use, there is no way we can do this. And the impossibility of this, so you can read the proof in the original paper, but I think there's like a very nice conceptual impossibility here, which I really, really like. I think it's one of the nicest impossibility ever in the whole cryptography. So the reason that this happens is, I think the nicest way I can put it is this, is asymmetry in time. And the reason is that, so this is a two-party protocol. Someone needs to start first. And it turns out that whoever starts first, they will lose some advantage in this protocol. Like making this into a full impossibility proof is actually quite cool, but the underlying reason I found really, really nice. So this is like because of causality in some sense. And so the thing is that this protocol, you can abstract it. Do you remember I talked about the notion of transcript in the first lecture? It's like this series of things that goes back and forth that makes like a whole protocol. So you can think of a very complicated transcript that goes back and forth between Alice and Bob. So this this is Alice and Bob, and so let's say the protocol starts with Alice, right? So Alice says something, Bob does something, says something, you know, like this goes and goes and goes and goes. And well, you say, okay, this cannot go forever. So at some point, I like put the limit and say, okay, this is the end of my protocol after m steps, right? And well, it turns out that no matter what you do here and here, if Alice is the one to start, at some point, Bob knows something about Alice's bits, and that will allow Bob to bias the protocol in the direction that they want. And so this is basically the reason. And there is no way you can do that even with some bias, and that's the more surprising thing. Like it's it's kind of like maybe intuitive why you cannot achieve that with a zero bias, but you can achieve it with any bias. So you can always cheat in this protocol. Like one of the parties can always cheat. Like maybe one good exercise to think about why this can happen is that assume that they use one-time path. So they need to somehow use some sort of encryption because, okay, plainly, if Alice flips a coin and says, okay, here my bit is 0, then Bob can say, okay, then, so let's say Bob wants 1, right? Bob can say, okay, my bit is 1 because he knows Alice's bit, he knows his bit, and let's say they agree on one-time adding their bits together. Okay, makes sense? So the moment I know Alice's bits, then it's done. I can cheat. If they both act, so I made let me write it down. So let's say the protocol I propose is that Alice flips a coin, gets paid bit A. Bob flips a coin, gets bit B, and the final bit they will agree on will be A XOR B. Now, if this is a random bit, this is a random bit, this is going to be a random bit. Even if one of them is a random bit, this is going to be a random bit. So the randomness is not the issue. The issue is that, well, you know, someone needs to tell the other party what's the bit. Otherwise, how are they going to calculate this together, right? And if Alice says it, then Bob will change his bits. If Bob says it, Alice will change his bits. So there's no way this works. And you can generalize that to many rounds, to all complicated stuff, and this still never works. But this is the yeah, okay. I put this to bed. Alright. So that's that. Yeah. You can do that if you, again, like similar to bit commitment, if you're happy to have computational assumption, this is achievable. And for instance, if you have one-way function as your assumption, then you can do that. Okay, how about quantum connectivity? So, the first protocol that tried to like take this functionality and do something quantum with it was this protocol. By Mayers, 1999. Funniest story is that many years later, we break this protocol. So the reason was that the protocol didn't have a complete security proof. There was like the protocol was introduced, and in the paper they just okay, this is the best attack, and here's like the probability for this best attack, and hence the protocol is secure. And yeah, it was kind of funny. So this guy is my friend Brian. He was doing his PhD in quantum machine learning when I was doing my PhD in cryptography, and he came to me once. He was like, "Okay, so I'm trying to do quantum machine learning for a completely quantum problem." And we were thinking together, okay, what is the complete quantum problem? And one of the things that came to our mind was cloning. So we're like, okay, approximate cloning is not like a classical functionality. There's no classical data here. The data is naturally cloned. And he wanted to do this variation, so using like, variational circuits, which people use in quantum machine learning to achieve approximate cloning. And so we were like working on this together a bit. But then he was like, okay, is there any like useful lessons? This feels like pretty useless. Like, can we find like an application for this thing that we're doing? And I was like, so at the time I was like working on cryptography analysis. I was like, okay, let me see if like there's a protocol we can like possibly say something about, you know, the security. And well, the first thing you can think about is PKD. I told you, like the cloning, the approximate cloning attack gives like the best bound for incoherent attacking PKD. So this is something you can do, and the application for this, if you do it with variational circuit, which is what we did, is that on a noisy hardware, which you know you can find better circuit that actually achieves that like threshold. While as if you just run like a, you know, the normal theoretical circuit, because of the property of the circuit, it might give you like very bad results and things like that. So you can kind of like show that you achieve that threshold. But then we were like, okay, we were doing different types of approximate cloning, and one of them is when you want to clone two non-orthogonal states. You don't want to clone any state in the block sphere. There's only two of them, and you want to do that. And so I was reading about point flipping at the time, and I was telling her, I think we can maybe like try to use that for cryptanalysis of point flipping, and that's what we did. And it turned out that this protocol actually completely breaks if you use state-dependent cloning as an attack. And then you can do it variationally, and you can use the best circuit that runs on your hardware and stuff. So yeah, so that was the story. I think that the reason that like we didn't became like very famous or something by doing that was that no one really cared about this protocol, because 1 year after this there was another protocol by another point flipping protocol, and that protocol actually had like full security proof, and the protocol was really nice and simple and beautiful. So like yeah, no one really bothered to go back and break Meher's protocol. We just did it for fun. But this is my take-home message to you, that prove your protocols properly, because maybe many years later some kids will come and break your protocol for fun. So prove your protocol very rigorously as good as you can. So a hard protocol it's quite nice. It doesn't achieve perfect bias. It achieves bias 36% for Bob, 42% for us. So for us it's quite high, but you know still is less than 50, so it achieves something. And it uses two pairs of non-orthogonal states to do this like encoding and stuff. So I'll tell you before. Then in 2004 there was another protocol by unbiased, and it's kind of like the same spirit, but they use QDIDs, specifically D=3. Yeah, so I would make Jackie very happy, I think, by showing this slide, that there are things that you can do so much better with QDIDs that you cannot do. QDIDs is one of them. So this is a protocol that, first of all, it achieves a bias that's symmetric, so this is good, and like much smaller, so like 25% for both of the parties. So this is really, really nice. So I'm going to show you this protocol, also to make Jackie happy. Okay, how does it work? As you might have like already started thinking about this, Alice needs to send something to Bob in terms like in the form of a quantum state, and it should be such that before a certain point in time, Bob should not be able to like read that value that's encoded in that state. So we use 4 states because we need 2 bits to achieve this, right? So bit A, which is Alice, is going to be, which one is this? So A is the actual bit, yeah. So A is the actual random bits that Alice will use later for the, you know, like they will use later for like as their random bit value, and X is just to select the bases. So so these are the states 0, 1. So this is plus and minus. And this is plus and minus in a, you know, between dimensions 0 and 2. So you have now, because it's a Q-treat, you have your bases being 0, 1, and 2. Okay? So let me do something. Let me write this state on the board. I want to ask you to do something later. 0, 1 for 0, 0. So this is X. Then you have +2 and the rest. Just like that. And so how is the protocol? So Alice was encoding, and then she sends the state and waits for Bob to send his value. So Bob needs to flip a coin and send the value. Okay, so now Alice has A and B, has both A and B. Bob still doesn't have A, right? He has the state. So then Alice needs to reveal something. So Alice will send both A and X to Bob. And so Bob has the basis and has the value. So he measures on the right basis and checks the value. Right? Does that make sense? So I measure in the basis that I need and I check the value. So that's my verification. If they both pass, now Bob also has A and X and has his own bit, which is B. So they can both just like export A and B. Right? And if I want to make that more secure, instead of like one bit, I can send like a bunch of these and then they like export all these like values together. But even with one bit. Is the correctness, like the reason that this is a coin flipping, is this part make sense? We'll get to security later.
Is it possible to bring the data next to Bob? Or in the third part, is it sending them?
No, in the first part, Alice is sending the state, not the, so the X and A are encoded inside the state. So I give an unknown state to Bob, and Bob, you know, like, if he wants to get the bit A, he needs to measure. But you can already see the problem. If he measures, then he cannot take Alice later. So he will not measure before Alice like sends her bits. Does that make sense?
Some form of
Is what?
some level of critical.
Exactly, that's a very good observation. So even classically, if you have bit commitment, you can construct coin flipping from it. It's the same in quantum. So if you had perfect bit commitment, you could do that. And yeah, in some sense, this achieves some level of bit commitment. The reason that this works for coin flipping is that you don't need perfect hiding and stuff. So you just need some level of hiding so that after you can like reveal and verify. But if you have bit commitment, that's it. So that's a very good point. In Arnold's paper, they also talk about the commitment version, and they talk about that. Okay, so this is the protocol. Let's look at the security a bit, because at least one side of the security is really fun, I think. Let's see how Bob can bias the protocol, right? So what does Bob have? Bob has a state. He doesn't have anything else. Like before he sent his bit, he has nothing else than a state. He knows that this state is one of these four states. He knows that this state encodes these values, right? So what can Bob do? So if Bob somehow from the state can read Alice's bit, and remember, it's the bit A that he cares about, because the X is just for the sake of the equaling. He cares about the bit A, right? If somehow he can get information about the bit A, so if somehow he can get information about bit A, then he can bias, right? So as much as information he can get about, like, the more probability or confidence he gets about bit A, the more he can bias the protocol. So the strategy is that he needs to make a measurement, right? But he needs to make the best measurement that he can. And how does that measurement look like? So now it's where you're gonna like be very happy that density matrices, because this is the only way to like be able to like encode this problem. So he needs to like distinguish between when Alice makes the choice of A being 0 and when Alice makes the choice of A being 1, right? But there's not 2 states, there are 4 states. So these 2 scenarios, they consist of mixtures of 2 states. In this case, whichever state I have that has a bit 0 it will be here. So the density matrix of uniform mixture of psi 0, 0 and psi 1, 0, it's 0, and the uniform mixture of 1, 1 and 0, 1 is 0. Okay, and now so he has two density matrices, and we need to understand with what probability, if Bob does the best measurement that Bob can, they can distinguish between the two. But we already seen this, right? You remember? I told you everything I show you has a consequence. Here's the consequence. So this is the whole level bound, whole level Hellstrom bound, and it tells you what is the best distinguishing probability between two density matrices. This is exactly what you have. You have two density matrices. So what I want you to do as an exercise is to write down this density matrix, calculate the trace distance, and find that this probability is 25%, because you already know the answer, but like do this exercise, it's really fun. And it's kind of like very easy once you know the whole level bound, and yeah, thank you for this. And yeah, this gives you the box attack strategy. And you realize that this is information theoretic, right? So the proof that I'm getting for this, it doesn't rely on anything other than quantum mechanics, so it's like really beautiful, I think. Listen. Yeah. So is the exercise clear? Okay, so do that. This is all right. So how about Alice? Unfortunately, doing this for on Alice's side is a bit more complicated. The reason is that Alice is the one who is sending the state, right? So she has a lot more options. It's not like, you know. So the way Alice can cheat is to send the state, which later, when Bob verifies, and you know, like after she receives, let me go back to the protocol to show you what I mean. Okay, so she's sending this state, and the way she can cheat is to not to prepare this state, but to prepare different states in a way that after Bob reveals, she can do something like partially on her state and change the state to something that passes on Bob's side. And if you remember about like the attack I told you on the commitment, this kind of like looks like that. So it's a bit scary, right? Because if Alice can send a state and she can do something locally that changes the other state. Struggling with this mic, I don't know. Maybe I can keep it like this. Yeah, no, I'll just keep this. Okay, I think it's better. Yeah, so where are we? Yeah, so if you can basically send something that so this doesn't, because Alice, remember, it's fully like malicious, right? So she can send like an entangled state, let's say, that when Bob receives it and sends his value, then Alice can do something locally on her state and then change the value to something else. So Alice's strategy is more complicated, but you can show that you can still bound Alice's success probability by kind of like assuming, like having this assumption that, you know, Alice wants to win no matter the bit is going to be 0 or 1. So it's like there's a symmetry between 0 or 1. And if you pick something that's like really good for one side of this strategy, it's going to be really bad for the other side. So the thing that is this helps the protocol work is that this symmetry. So if Alice symmetrizes all her choice of all the density matrix that can possibly pass this protocol, then you can, so then you can basically see that like those density matrices, they cannot win more than probability 3/2. So more than this, she will get caught. Bob will know that this is not the right density matrix. And that's how the proof for Alice works. But it needs a bit more work and a bit more like quantum information to be used to get there. But it's, you know, conceptually it's not that hard. Okay, and so these are two protocols, and obviously so we went from a protocol that's like fully broken to something that's like 3642 to something that's 25. So the question is that, can quantum solve this problem fundamentally? And this was answered yeah, so the answer is no. So unfortunately, this is another thing that this quantum is also limited in. So you cannot achieve perfect, strong point flipping. So this is also an impossibility. And interestingly, there's like a bound for that. Like what is the smallest bias that a quantum protocol can possibly achieve? And this bias is this. And this isn't shown by Kitaev. And the proof for this, I'm not gonna even try. So this is hard. This like needs like STP basically to optimize like all kinds of like density matrices and get there. And so it's like a complicated proof. You might notice that. So the reference I'm putting for this is this paper, and there's no Kitaev here. And the reason apparently, like I was very curious about this. I was like, where is this proof? And I was like searching for it for a while. And apparently the story that Kitaev does this proof in a conference, and he never writes it down. It's just like can't be bothered. Just does the proof of the most like interesting thing of that year. It was like, here's the proof, by the way, bye. And then later, like these guys, Andrew Shayu and Jordanos, they kind of like write it down in this protocol, and they also give like some optimal protocols that achieve this and stuff like that. But yeah, the proof was done by Kitaev apparently. So yeah, this is this like fundamental beautiful bound of square root 2 minus 1 over 2. That like this is the best bias you can achieve by coin flipping. Cool. There is a variant of coin flipping which is called weak coin flipping, and the only difference is that the values are determined. So you just make this simple assumption that, let's say, Alice always wants 0 to be her win bit, and Bob always wants 1, or the other way around. It doesn't matter, but it's just that you assume that this is predetermined. In a strong coin flipping, this is not the case. So it's like Alice wants to maybe wants 1, maybe wants 0. You don't know. Like you still want to achieve. So this is called weak coin flipping, and weak coin flipping is still impossible classically. Like this assumption doesn't help. But now the magic comes, and here's when like things get very different. In quantum, you can do that, and this is like where the impossibility breaks. So this was shown 2007 by Mochan in this paper, and showed that you can achieve arbitrary small bias, like not 0, but arbitrary small. Like you can like repeat this protocol many times, and asymptotically you can make the epsilon very small. But the problem with this was that this was not a constructive proof. This was an existence proof. This shows that a protocol exists that achieves such bias. It's like you don't know what the protocol is. And so this was open for a long time in the community. This is one of this like open problem of quantum crypto till 2019, which Atul Singh Arora solved this problem really beautifully. And they achieve a bias, I think it's like around 1/10 or something. And this is like a concrete constructive protocol. Still achieving the like the smallest bias, like arbitrary small bias. I don't think we have like a concrete protocol that achieves that. So this is still like people are still working on coin flipping for all these reasons. And there's like a lot of interesting research that's happening in this area if you're interested. And the last thing for experimentalists is that this has been also shown in the lab. So I showed these 2 papers. So Eleni and like some other people. So they show like I think both the strong coin flipping and weak coin flipping. They demonstrate like some protocols that does that in the lab. They don't show the Atul's protocol though in the weak coin flipping. They show another protocol. I think it's like a like the bias maybe it's not as good, but it's easier to do in the lab. So it's one of the things you can actually do and achieve. And so last thing is that coin flipping also similar to bit commitment, you can construct functionalities out of that. So this is one of the, it's not as strong as bit commitment, but still there are a lot of functionality you can build on top of coin flipping. And I think that's it. So that's this part of my lecture. So we'll come back for the rest later. Any remaining questions? Yes.
Yes. So
Will use one card?
All right. So my question is about the biases in the coin flipping problem. So, for example, in this scenario, the bias is 1 in 4, right? So if both players cheat, do they both get like 75% chance?
If
It's like impossible. So
So the protocol tells you that basically each one of them can get has a 75% chance of winning.
how is this possible? If they both cheat, they can both get 75% chance of getting the
So okay,
desired
I see
result.
what you mean. So so usually like because in this setup you need to analyze the so in the setting that at the same time they're both cheating, you cannot really analyze the security. So usually when it's the same for bit commitment, you analyze the attacks one by one. So you say, okay, if Bob is honest, Alice is cheating, what is the probability? And then you do the other side. Bob, like Alice is honest, but so. You see what I mean? So you analyze the security for when one party is honest, one party is dishonest, and then you do the other way around. And the worst case of these two will be the final bias of your protocol, because this can always happen. That's how you can think about it.
So, anyways, if both cheat, can you even like analyze this scenario?
But the thing is
or
that
can it like turn out if it's like they both cheat? Actually, they both get like 1/2, and it's all like it's all equal now. So they are like they prefer to cheat. Both cheat.
They both cheat to no.
To
that's
like kind of
not
cancel each other out. No.
No, not really. Because so let's have a look, for instance.
So like even is this even possible to analyze if both cheat?
Well, as far as I don't know, but let's see why. So this is not me saying no. So let's say they both want to cheat, right? And Alice in some states that's not the real estate. Okay. Then Bob is trying to like verify that state, right? So Bob will try to verify that state to be able to catch Alice, right? And he needs to extract like that information as well, right? So he needs to kind of like, so Bob, okay, let me put it this way. Bob has one state. He needs to either use it to catch Alice or to cheat. He cannot do that. He cannot do both at the same time.
Mm-hmm.
Like in this protocol that I'm showing you, this is obvious why you cannot analyze the security as like Bob at the same time is on it and is cheating. Does that make sense? Mm-hmm. Because like I give you one state, you can like measure it to, well, you need to measure it, right? But either you're trying to catch Alice or you're trying to get the information and cheat.
Yeah, maybe so. If it's like actually preferable for both parties to cheat, they probably both know that and they're pretty sure they both cheat, so Bob would just abort the protocol every time and not come to a conclusion.
Oh, okay. That's a different story. So there's another attack. So this attack that you're saying exists in many protocols, and a lot of times you cannot avoid that, and that's like the always abort attack, right? So there is a way to break many of the protocols by one of the party just like aborting, and then like aborting and also get some information. But this is not part of this analysis. Like you don't take account for that attack because that will break the protocol always anyway. So this is not a viable attack. But I think your other question is interesting. The question is like if they both try to cheat, is there a chance that the protocol becomes honest?
Yes.
I don't think that's the case. And the reason is exactly because there is this it's the same thing for Alice, right? So she cannot really like try to like either she needs to be honest and send the right states, or she's cheating and she needs to send the wrongest state. Like there is not really a way that she's like both honest and dishonest at the same time. If that makes sense.
But she knows that if she's honest, then Bob can utilize this to shift the favor on his side. She would never be honest, right? She would always cheat, and in cases in which she does get caught, she just does that again.
Yeah, sure,
until Bob allows it, and
but
that's
so
it.
another thing that you need to maybe that like helps to understand what I'm saying is that when you analyze the security against like one side being honest, one side being dishonest, you capture all possible attacks. That's how it works, right? So you go for the best, like the limit of the best possible attack. And so the thing is that now whatever would have happened even in the case that they were both dishonest is already captured in this scenario, right? Because what you're checking, for instance, when Bob is dishonest, let's say, you're checking for the best attack that Bob can possibly do. So now this also takes into account cases where, you know, Bob has something else and tries to attack. So it's kind of like there already. So there's no possibility for something to achieve better. But I think your question is more like from the practical side. So this way is more for the security analysis side. So you kind of like divide the parties to be able to analyze the security.
Yeah. So theoretically, yes, this captures like the whole range of possible outcomes. But yes, but in practice, what is the actual like chance?
They can both attack, and that's a valid question. There are some protocols. I think actually the one by Anders Shayu and Jordanes. Which one is no, this one. Where did I have it? Yeah, so this one. So the one that's been discussed here, or like there's another one called cheat sensitive coin flipping. So there are some protocols that they have different mechanism for checking, for verifying and for catching the cheating party. So there's basically two sets of measurements. One of them is for verification, one of them is for extraction of the bits, and then you check for both of the outcome of both of the measurements. And so those protocols, maybe like it kind of answers your question. They design in a way that they're cheat sensitive, so you can you can capture the bias as well as what is the chance of you getting caught, and then give you two kind of separate probability, which you can also symmetrize to get something that's like close to this. But yeah, other than that, I don't know if I answered your question, but I think that's the.
It's kind of like a little confused still as to the practicality of.
I think maybe someone wants to comment on that, so I'll pass the mic.
Yes.
So it's maybe a follow-up from his question, but I was wondering if there's any link or work between this and the prisoner's dilemma. There's a bit more on the game theory side.
Oh.
That you know?
I don't know.
Okay.
Maybe there's, but does anyone know? Is there
Yeah, exactly. Yeah. So that's a bit of a follow-up question, yeah.
Okay.
Because it's more on the game theory side, but it seems like it would be suited somehow.
I don't know. I can have a look. But
Okay, just curious.
Good question.
Thanks.
Yeah. Okay, good. Then I'll bring it.
Okay, so I think you mentioned about using these as primitives for proving other cryptographic protocols, but do they need to be composably, proved? Because I think in the last lecture you mentioned about the ACUC framework. So are these proven that way, or?
It's not proven that way, but the impossibility will pass along. So that's if it's impossible here, it will be impossible in this. But there are, so the computational bit commitment, both classical schemes and quantum scheme, people do try to prove that in the UC framework or AC framework because of exactly what you said. Because if you want to build, for instance, two-party, multi-party computing on top of that, then you would need to make sure that this is secure. Otherwise, you'll have to use it inside the whole scheme and redo the proof.
Yeah. Thank you.
I don't know if it's still relevant, but I mean, I wanted to comment regarding this. What if both people try to cheat, right? But I think, at least as I see it, in the end, like a cryptographic protocol is just a set of instructions that if you follow them, you have some guarantee. And this guarantee is what we call security. If you don't follow these instructions, then anything goes, right? So if you cheat, then you have no guarantee at all. And the way I see this is that if both cheat, like anything can happen, right? They can, I mean, it can be completely biased for one side, it can be no biased, and this works for any protocol, of course. I think like it doesn't really make sense to think of a cryptographic protocol if no one follows the protocol, then it's just random communication, right?
So one thing I would add on that exactly is like you, even when you cheat, you still want to get the correctness of the protocol. So you still want the task to be done. So there are maybe strategies that you do, but that they don't achieve the task that you wanted to achieve in the beginning. So if it doesn't achieve that what you wanted to do, then there's no, I think that's kind of like, that's your point. There's no point in cheating, right? So you, like Alice and Bob, so if we go back to the original like story, they want to have a coin flip that they both agree on. It's just that Bob wants the outcome of the coin flip to be what he wants, for instance. It's not like that they want like something that is not a coin flip at all.
I was wondering, like, what would we expect bias to be if both parties cheat, like in the maximally optimal way, and also know that the other party also cheats, right?
So I think the bias won't change. Yeah, the bias won't change as long as the correctness is achieved. So let's put it this way: as long as the protocol achieves the functionality that it's supposed to achieve, the bias cannot be different than the bounds that you do in the proofs, right? So for unbiased protocol, if one of them cheat, or if both of them cheat, or if they both cheat at the same time, they cannot possibly do better than that's like 1/4 bias. That's the thing.
In essence, my question was like, in the tug of war, cheating, like who gets the most, like.
Okay, that you cannot know, or at least I cannot do that in the proof. That's why I'm telling you, like, you need to like keep one side honest, the other side, so that you can follow the protocol and analyze the security. But yeah, who will want more? I don't know. And that's the thing is that you always assume that's like, and that's like a general thing in cryptography. You always assume that the malicious party will do the best attack. So this is like some sort of reasoning you always carry on. So it's not like, oh, maybe there's this attack that is like optimal, but maybe they do something else which is less optimal. No, you will always assume that the worst thing that can happen will happen, and this is the thing that the adversary will go for. This is like an inherent assumption in all the crypto proof, I think. Yes.
Following up on this, I mean, I agree that there's not much like interest in considering two cheating parties for a one-shot protocol, but is there kind of security analysis either for coin flipping or other protocols where you do like, let's say the asymptotic regime, and you say, or like, you know, n rounds, and you say in k rounds there's Bob who cheats, and in n minus k there's Alice who cheats? Like, is there kind of some, can you do a security analysis in this way?
There are things like that. So first of all, there are analysis of the round protocols. These one, the weak coin flipping ones, these are like that. So these ones, like these and Atul's protocol. So these are all rounds protocols. So you need to follow this in multiple rounds. This is not achievable in one round, and you don't analyze. So this is the first part, and yeah, that's a good point, good comment. Although I don't know if they kind of like put these assumptions on. some parties are cheating some of the rounds more than the other. I don't think this is the case. I think you kind of like, again, assume that if when Alice cheats, they cheat as much as they can in all the possible rounds, and if Bob cheats, they cheat as much as they can in all the rounds, and then you do the analysis over the rounds, like after n rounds, because in the round protocol you will only get, so you're still getting only one bit of outcome as an outcome of this protocol, but you will do it after many rounds. So yeah, so then you need to do the analysis after rounds. You can analyze the security of this over rounds as well. So this is also something that has been done. But yeah, I don't think they kind of like do the majority cheating round party or something. But that's a good point. Maybe there's something interesting in that. I don't know.
Also, there seems to be ways of platforms.
So should we do this? I'll come back to you.
Yeah, so the slide you told about the distinguish between two density matrices for this coin flipping things using Hillstrom minimum error measurement. So what is the goal? Means the goal is to distinguish with maximum success probability, or there should be some conclusiveness as well? Because as I am thinking that Hillstrom minimum error measurement is not a conclusive one, so I think we should use some unambiguous state discrimination kind of thing. Because
should use what? Sorry, I didn't hear.
For distinguishing these two density matrices that you show in slide for this coin flipping kind of thing.
So you mean this? Like the exercise I give you. This.
Yeah. So this is the Hillstrom minimum error measurement that you are talking about.
So this is the whole Hillstrom one. Yeah. So this is the optimal probability of distinguishing between two unknown densities.
Yeah, so this actually distinguishes with maximum success probability, but the outcome is anyway inconclusive. Means you cannot tell specifically what are the instances for which you have guessed correctly. Means eventually.
That's enough. So you just need to distinguish between the two, because you want to know Alice's bits. You don't need to know the states, right?
We do not require conclusiveness. Means we should not need that for which instances I am telling correctly. Because for this, we need, I think, unambiguous state discrimination.
No, you don't need unambiguous.
Yeah.
This is the correct one.
Yeah. Because anyway, if we just guess randomly, then we will succeed with probability half. But in that case, also we cannot guess that for which instances I have guessed correctly. So I can tell that overall I have correctly guessed for half of the instances, but what are those specific instances I cannot tell.
I mean, if I understand it, so there's like a couple of things you said. First of all, that half probability, this is already embedded in the security definition. So if you go back to here, so you see this is half plus epsilon. So of course you can always like tell the bit with probability half. So half is there, right?
Yeah.
So this is not a bias. Like everything that's more than half gives you the bias value. So that's fine, right? But so about the second part, that like there's maybe that part I don't understand. So you don't really look for so in ambiguous state discrimination, you care about whenever you say like this is state or that's so say you have a state 1 and 2, right? So you have bit 0 and 1. So whenever you say this is 0, then you're right. Like there's no wrong probability. There is only I don't know probability. Right?
Yeah. So
but here this is not what you want. So what maximizes the success for you is to tell when you have bit 0 or when you have bit 1. It's fine that sometimes you're wrong. Right? If sometimes you're wrong and then you lose in that round, but the idea is that what is the probability that I guess this right? Because if I guess this right, there's an easy attack. I just flip my coin and I send it.
Okay, so that means conclusiveness is not a goal. I just want to guess is at much success as possible.
Yeah, exactly.
Okay,
so I just want to distinguish between these two cases. I don't want to really distinguish optimally between the two states because I'm not doing anything with the states afterwards.
Thank you.
Yeah, no, good question. Thanks. Mr. had a question?
Yeah, I just maybe thought way.
Let me get
I don't know whether it's like the correct way of thinking, but Because I'm not a cryptography theoretician, I'm thinking again about the practicality. So when Alice sends her bits to Bob, he knows like both bits and still needs to verify Alice's. So he knows what the result would have been if he were to agree, right? So if he doesn't like the result, he could just say, "Yeah, Alice is cheating. I'm not gonna. I'm not gonna prove." And then.
So when Alice is sending her bits, she doesn't know Bob's bit yet. Do we agree on that?
No. She knows both bits when Bob says his bit to her.
Yeah, but before this,
the roadblock is Bob actually who can abort the protocol at step 4. At step 4, he already knows both bits that would return the outcome A and B.
Yeah, so at the step 4, yeah, exactly. So she knows the outcome, but she already committed to her.
Bob, by the time the step 4 happens, Bob already knows C actually, like the outcome. If he were to agree on the verification,
yeah,
he knows the result. So if he doesn't like the result, he could just say Alice is cheating. He could lie.
Yeah, but if he says that and he lies and Alice, like they won't agree on the bit, so the protocol aborts. The security is not broken.
But if he does like the result, he says, yeah, it's okay. He doesn't even need to check anything.
I disagree.
So he can like shift everything in his favor. So why is that not like considered here? I know it's like a cheeky way of doing things.
I don't see the attack.
And Alice would probably also notice that, like, if they repeat it many times, she also knows both bits, right? By at step 3, right?
No, because
no, at step 2 already. So like she can notice that,
why would
Bob is probably lying.
Okay, wait. So first of all, this is a 1 round protocol. So there is this is 1 round.
Yeah.
If you are to, and it's the security that we analyze is also for 1 round. So the idea is that they do this 1 time and that's it, and they get the bits, right? So only once. So now the things that I was saying to him was that you can repeat this in many rounds and after that agree on the value of the bit. But if you do that, then in every round you have a new pair of A and X and B. Right, so we have now lots of coin flips, and then you add them all together, and you get 1 bit. Does that clarify? Maybe
so Bob needs to just wait until the outcome is whichever he likes, and then he was like, okay.
Yeah, if you do that over many rounds, then basically you aggregate all these results, and so here instead of XORing just 1 bit, you XOR 2 strings. Or I don't know, get not maybe 2 strings, you get the majority of all your bits and then you get 1 bit and then you XOR. So at the end you need to get 1 bit out, right? Not a string. But maybe you can do that multiple rounds, get a string and get the parity of that string, for instance. That's one way to do it. And then add the parities together and get the outcome bits. But this analysis of whatever we talk here is just for 1 round, and in 1 round this protocol is supposed to work, and it works with that bias that I showed you. So that doesn't really break.
It's also not security anymore. It's outside the definition of security. Just the definition of security is whether you can bias out.
Exactly.
Avoiding is not biasing out. It's just not following the protocol.
Yeah.
More like game theory of security.
Right, that's the whole idea. But then you might as well not just not answer the phone.
Okay.
Yeah.
You make all the strings you like, but the only outcomes decide for the protocols will be only bits that Bob liked. So it's also everything in favor of Bob.
It's not everything in favor of Bob. It's just that what you're describing again. I said it's just the fact that Bob can abort. It's not in favor of Bob because it's not in favor of any of them if they don't agree at the end of this protocol. Because remember, there was a reason they started doing this game, and they want to get the outcome at the end of this game. Now, the idea is that can they get the outcome, but on top of that, cheat? If they don't get the outcome, there's no point in cheating.
Oh, okay. So maybe I like imagine them being more evil than they actually are. Like they're not actively sabotaging each other.
Yes.
I think this is actually true, you can do this, but if you go, so let's suppose Bob awards in step 4, right? Just because he doesn't like the outcome.
Yes.
But Alice was honest. Because if they are both,
Yeah.
if they are both malicious with this card, this doesn't count. If Alice is honest and Bob doesn't like an award, Alice knows that Bob's not honest because he should not have a award.
Yes, that's what I was saying. Like Alice will also notice that, and
So
she'll probably go like, yeah, Bob is lying.
So that's okay. Because otherwise you could fight like that, that's great. You cannot do that without being taught that you are reporting when you should not be reporting. That would be a problem.
But the whole point is that the abort is not part of the game. Like if they abort, they have not achieved the outcome.
Right, if they are both honest.
Yeah. Yeah, if they're both honest, they should not abort, exactly. But yeah.
So I imagine initially Bob's thinking like, I'm not gonna let you achieve any result except the ones that I like. It's like the maximally sabotaging like options. Like I'm gonna abort everything.
Yeah, but it would be like, you know, then in that case they will not run the protocol, they will fight. That's the way to do it. So this is cryptography to avoid fighting. I would say. Okay. Cool. I think it's time for a break.
Yes.